We're Group 5, and this is our Pasta Bridge presentation. I'm Nico.
I'm Nicholas.
I'm also Nico.
I'm Rob.
All right. So we have been contracted by NASA to design a bridge that could be used on Mars in order to cross large gaps. Now, because the bridge would have to be created out of a 3D printed material that would be really the only thing that they would have access to, we decided to create our model bridges out of pasta in order to simulate that limitation. Furthermore, our bridges, in order to model the actual requirements for the bridge, had a weight requirement of 125 grams. They had to be able to cross a 30-centimeter gap, and they had to have a walkway large enough to accommodate a 4 by 1.6 centimeter figure.
For our background research, we initially looked at the Tacoma Narrows Bridge collapse in Tacoma, Washington. That was a suspension bridge that famously collapsed in the 40s. From that, we determined that the suspension bridge was not an optimal design for us, so we went with the truss bridge design, which seemed to be the most ideal for us in the situation. It's one of the most common and reliable bridge types, dating back all the way to the 17th century. It has a fairly simple construction, as it's mainly made out of straight lines and sharp angles. It has a very high strength to weight ratio, and critically for this scenario, it does not require any base pillars or cables, which would be hard to construct over this crevice on Mars.
So the first truss bridge variant that we looked into is the bowstring truss. The advantage of this particular truss bridge is that it has a rather stable foundation. And the other main advantage of this is that the archway over the top of it and its supports provide evenness between compression and tension, which allows for a better distribution of weight, which should provide, in theory, more stability. The other advantage, too, of this bridge is that it is very economically and material efficient, so it's rather easy to build and it's cost effective.
The next design that we looked at was the Pennsylvania Truss Bridge, which was named that because of the Pennsylvania Railroad Company, which used it for a lot of its bridges. Like the previous bridge, it prioritizes material efficiency for strength to weight ratio and things like that, but it also critically places extra trusses along the bottom in order to help further protect against the weight, which would be largely centered around the bottom.
The third bridge that we took a look at was the Pratt Truss Bridge. It's a widely accepted and used truss design. It focuses on spreading out tension among all of its struts. It's cost effective due to a low material requirement. It's well suited for when a mixture of loads are used, although it does have a hard time dealing with non-vertical loads.
The last bridge design we looked at was the Warren Truss Bridge, named after James Warren. It uses equilateral triangles in the middle to evenly distribute large loads of weight. It's a very simple design because of all the straight lines and even-sized parts. It has few materials, which will be a cheaper option for us, and it also can spread, like I said, it can evenly spread load across the entire bridge. Its downfall is that it struggles sometimes with having a concentrated weight in one specific part of the bridge.
This is our Gantt chart. It chronicles all of our efforts across the entirety of the project, from ideation to testing to presenting. It shows all assigned tasks, what memo they were for, when they were started, when they were finished, and to what degree they were completed.
This is our cost and material table. This particular table shows the products we purchased for use in this project, their cost, quantity, and where you can buy them. In our case, we were able to secure the bucket and the weight from Phylec, so it only came out to be approximately $50 total for us. However, if someone was to try to replicate our project from home and did not have those school resources to get those parts for free, it would come out to be about $70, as shown in the total section of the table.
For our testing, we went to the Filix Center on the 3rd floor of Snell Engineering. We did it in the hallway, setting up two trash cans 30 centimeters apart to simulate what we would be doing on Mars on a larger scale. We had a cardboard piece with a string through it and used that to suspend a bucket from each of our bridges. The bucket hung beneath the bridge, obviously, as you can see in the picture, and we added water slowly to the bucket for each bridge until there was either collapse.
For the bowstring truss, it came out to be 30 centimeters long, 10 centimeters wide, 12 centimeters high. It had a weight of 38 grams, and it ended up holding 366 grams before collapsing. The feedback received from peers about this particular bridge was that it had a sturdy base, good glue work, that it appeared to be a bit flimsy, but overall relatively sturdy, and that the archway there was a bit tilted.
Right. So for the Pennsylvania Truss Bridge, it ended up having a length of 35 centimeters, width of 5 centimeters, and a height of 10 centimeters, and it weighed 47 grams. The bridge collapsed in on itself after holding about 962 grams of weight. And some peer feedback was that the paper, which ended up stuck to the bridge itself during the gluing phase, was very messy and looked unprofessional, but the glue work itself was good looking and the bridge overall looked somewhat flimsy.
The Pratt Truss Bridge ended up having a length of 30.48 centimeters, a width of 3.81 centimeters, a height of 5.08 centimeters. It had a weight of 30 grams, and it held a total of 611 grams. Some peer feedback I received were that the bridge had clean, straight lines, scattered glue globs, but a sturdy design, although it was a bit on the light side.
For the Warren Truss centimeters, the width was 10 centimeters, the height was 11 centimeters, the overall weight was 67 grams, and it was able to hold 526 grams before collapsing. Some feedback from my peers were that the bridge seemed slightly flimsy. There was no glue globs on the design and had fairly straight and clean lines, but it did not hold much weight, only about 8 times its overall weight is what it held. And there you can see the comparison between the pictures, the real design, and the design sketch.
After reviewing our peers' bridges, we noticed a handful of things about them that we thought were very good and that we wish that we had emulated in our own bridges, which were that the bridges were typically on the higher weight end, which means that our peers tended to take advantage of the higher weight capacity for the bridges in order to create ones that were more stable. The next thing that we noticed was that the designs were much cleaner, so the line work was very neat and concise. The third thing was that the glue work was very well done, so everything was bound together really well without being messy, so the presentation of the bridges was overall very clean looking because of that. The bridges were typically smaller and more compact, which allowed them to hold more weight because they were, more close together. And then the last thing we noticed was that all the bridges had a lot of supports on them, so the weight was clearly distributed between all those supports very well and very evenly, which allowed for them to hold much more weight.
Yeah. As far as the other group's methodology goes, they did a very good job. They had strict, controlled methods for testing. It was all very standardized. The one issue that overall was that for all the groups that we saw, they tended to they tend to add water in solid increments rather than gradually adding it little by little, which could have slightly thrown off their measurements for how much water it would actually take to break the bridges. Otherwise, all good though.
From looking at our testing results, it's clear to see that while our bridges design show promise, each bridge is praised but plagued by a handful of fatal flaws. were we to do this again, we would account for those flaws. One present number, a fraction of the max weight limit. No, the bridge that weighed the most weighed only 67 grams, which is far below the weight cap of 125 grams. It's safe to say if we scaled each of our designs up to make full use of the weight cap, our designs would perform significantly better. Another change we would make would be to use hot glue rather than Elmer's glue. Our group members found Elmer's glue to be hard to work with and a bit unreliable. To rectify this problem, partly through construction, some of our group members switched to using hot glue to make up for the Elmer's shortcomings and found it to be a far better adhesive.
As a summary of our results of this project, we determined that the Pratt and the Pennsylvania trusses had the highest weight to strength ratio. They were able to hold about 20 times their weight each. So if we were able to scale that up, that would be the most ideal design, because on a Mars mission, we do not want to spend a lot of money on heavy materials or using a lot of materials. And so the smallest amount of weight holding the largest amount of weight is obviously the ideal design. Both of the designs and all of the truss bridges are fairly easy to assemble because of their straight lines, and it would be feasible for astronauts or whoever's on Mars needing to construct this large bridge across the crevice.